Okay, this is the second of two pre-recorded lectures on Taylor-Maclaurin series. The focus today is to give it a function f of x, compute its Taylor series. Now, just as a recap from last time, this is a formula for a Taylor polynomial of degree n with center x naught. For this, you have to evaluate derivatives of f starting from the function itself, first derivative, second derivative, up to the nth derivative at x naught divided by j factorial times x minus x naught to the j. Now what we have here, this polynomial of degree n has n plus 1 terms altogether, and these are the first n plus 1 terms of the Taylor series. So what we'd like to be able to do is compute all of these terms, all of the coefficients. Now that can be done if, for a given function, if you go ahead and compute the first few coefficients, maybe you can see a pattern that will help you get the rest of them. Here's an example, e to the x. If you were to compute the first few terms of its Maclaurin series, in other words, its Taylor series centered at x equals 0, what you would get is all the coefficients are just 1 over a factorial. So we can deduce what the entire series is from there. Now, also, if we compute a Taylor series, we'd like to be able to determine its radius of convergence. If x is outside of the Taylor series interval of convergence that's determined by that radius, then we should not use the Taylor series to approximate, because and the also the Taylor remainder doesn't go to 0 as the degree n goes to infinity. All right, so as an example, here's our function f of x equals 1 over x. So if I were to compute derivatives of this, so first derivative would be, because you can think of this as simplified differentiation, 1 minus x raised to the minus 1. So if I use a power rule on this, I'll get minus 1 times 1 minus x to the minus 2. But then by the chain rule, you have to include a minus because of a minus x, which cancels the minus that comes from bringing this exponent down. So you end up with plus 1 over 1 minus x quantity squared. Now, if I take a derivative of this, using the power rule again, I'm going to get this factor of 2 that comes from this exponent here. And this pattern could, and then if I took the derivative of this, I already have this 2 here. Using a power rule will introduce an additional factor of 3, giving me 6 for the third derivative. In fact, I'll go ahead and fill that in here. So f triple prime would be 6 over 1 minus x all raised to the 4th. So in general, you have, for the nth derivative, you have n factorial, because notice 2 factorial is 2, 3 factorial is 6, and so on, divided by 1 minus x raised to the n plus 1 power. So I have the information I need to get my Taylor series at whatever center I like. So if I plug in x equals 0 into this, I'm just going to, the denominator will become 1, and I'm just left with n factorial. So this is n factorial, which cancels with the n factorial that's down here from Taylor's theorem. So I'm left with x to the n. Now that's just the geometric series, as we've seen before, where a is 1 and r is x. So this geometric series will only converge if the absolute value of x is strictly less than 1. So we have a radius of convergence of 1, and this is the interval of convergence. Right. So the function 1 over 1 minus x, you can evaluate this function at any point except for x equal 1. But only for x in this interval can you use this series representation of it. All right. Next example, f of x is sine x, and we'll continue with center x equals 0. So here are the derivatives. So you take a derivative of sine, you get cosine. Take a derivative of that, you get minus sine, minus cosine. And then take a derivative of that, and you're back to sine. So all the derivatives cycle through these four functions: sine, cosine, minus sine, minus cosine. So in general, you can say this, that the 4nth derivative of sine x is sine x, where n is any non-negative integer. The 4n plus 1 derivative is cosine. 4n plus 2 order derivative gives you minus sine. The derivative of order 4n plus 3 would be minus cosine. So I'm just extrapolating from what we have here. Now, if I substitute x equals 0 to all of these, well, sine of 0 is 0, and cosine of 0 is 1. So it turns out that all the even order derivatives of sine at 0 are 0, and all of the odd order derivatives are equal to plus or minus 1. Or I can condense it like this. So for example, the first derivative corresponding to n equals 0, the first derivative is equal to 1. The third derivative is equal to minus 1. And then fifth derivative would give you 1, seventh derivative would give you minus 1, and so on. So another way to describe that is that the odd order derivatives, so any derivative of order 2n plus 1, is equal to minus 1 to the n. So for instance, if I set n equals 0 in here, I'll get 1. If I set n equal 1 in here to get the third derivative, I would get minus 1. So I'd have this alternating pattern here. So since all of these are 0, I'm only going to have odd powers of x in here. So I'd have x to the 2n plus 1 divided by 2n plus 1 factorial. What I need here is the 2n plus first derivative of f at x equals 0, and that's its minus 1 to the n. So that's what goes here. And now I have my Maclaurin series for sine x. And if you were to apply the ratio test to this series, you would find that it converges for all x. In other words, the radius of convergence is infinity. The interval of convergence is minus infinity to infinity. We can do the same thing with cosine. Its derivatives have the same kind of cycle of, so cosine gives you minus sine, then minus cosine, then plus sine, and then you're back to plus cosine. So then if I evaluate all of these derivatives at x equal to 0, all the odd order derivatives will be equal to 0 because sine of 0 is 0. All the even order derivatives are plus or minus 1. Another way of putting it is all the even order derivatives of order 2n are at x equals 0 are equal to minus 1 to the n. So that describes this pattern here. So now the Maclaurin series for cosine of x, I have only even powers because all of these coefficients are 0. So I'll have x to the 2n over 2n factorial. And then what goes up top is the 2nth derivative at x equals 0, which has been found to be minus 1 to the n. Okay. Actually, I want to go a little further to explain where this comes from, and the same reasoning would apply to the previous example with sine x. So here, if the order derivative is 4n, I get plus 1. Another way of putting it is that the order derivative is 2 so 2 times 2n. So in other words, it's 2 times an even number. Over here, I have 4n plus 2 order derivative is equal to minus 1. If I factor a 2 out of this, that's 2 times 2n plus 1. In other words, it's an odd multiple of 2. Now, this expression, as we've seen before, is equal to plus 1 if n is even, minus 1 if n is odd. So since we see here that order derivative is 2 times an even number, we want 1. 2 times an odd number, we get minus 1. So that's what leads us to using minus 1 to the n down here. This series for cosine x also converges for all x. So here's radius of convergence and then the interval of convergence. All right. The remainder of the examples in these notes are all based on online homework problems that you've been assigned. Because now that we have these series for certain fundamental functions like e to the x, sine x, cosine x, we can use those series to get series for related functions. Like in this example here, I have f of x is 10x squared sine 10x. So I can use a series established earlier for sine x as a starting point. Excuse me. So here's that series for sine x reproduced. And what I'm going to do is first, I'm going to work my way from this function to this function. The first thing I'll do is replace x by 10x. And that's what I've done throughout here. So I have this extra factor of 10 to the 2n plus 1 that goes with my x to the 2n plus 1. And that's a series for sine 10x. So you can make that substitution. Now, if I multiply both sides by 10x squared, both sides of this by 10x squared, now on the left side, I have a function I want. I have my original f of x. And here I had 10 to the 2n plus 1. I multiply by 10. That adds 1 to the exponent. So now I have 10 to the 2n plus 2. And then I multiply this power of x by x squared. So now I have x to the 2n plus 3. And because this is sort of thing that the homework asks for, here are the first few terms of that series. Notice we start at x cubed because we have x to the 2n plus 3, where n starts at 0. So my first term is going to have x cubed, and then I'm going to have x to the 5th, x, all the odd powers of x from that point on. And just working out what these coefficients are gives me these values here. Now, the series for sine x converges for all x. So replacing x by 10x, in general, that does change the radius of convergence. But because the radius of convergence is already infinity, it's still going to be infinity. Multiplying by an expression like this, constant times the power of x, in general, does not change the radius of convergence. So because the series for sine x converges everywhere, this series does too. All right. The next example, similar nature. My function is 9x squared times e to the minus 8x. So my starting point is the Maclaurin series for just plain old e to the x that I have here. So then I will replace x by minus 8x. So that gives me this. And then I'll multiply both sides by 9x squared. So I'll have my original function f of x that I want. So that 9 sits here. And then I've broken this up into minus 8 to the n times x to the n. Then I take that x to the n and multiply it by x squared. So now I have x to the n plus 2. I'm going to rewrite this as minus 8 to the n x to the n. So if I plug in the first few values for n, and n equals 0, 1, 2, 3, I get my first term is going to involve x squared because I have x to the n plus 2 here. So these are my first 4 terms. And again, because the series for e to the x converges everywhere, this series also converges everywhere. Now, if I had a function whose series had a finite radius of convergence, capital R, and if I replace x by 8x, what that does is that reduces the radius of convergence by a factor of 8. This is that because the original radius of convergence is infinity. If I divide that by 8, I still get infinity. All right, next I have f of x is 4 to the x. So because this is an exponential function, I'm again going to use the Maclaurin series for e to the x as a starting point. And then what I'll do is use property of logarithmic functions to rewrite 4 to the x in terms of a natural exponential function. So I can write 4 to the x as e to the log 4 to the x because e and log are inverse functions that would cancel. But then if I look at ln 4 to the x, one of the properties of a logarithmic function is if I'm taking a log of something raised to a power, I can bring that power down over here. So now I have e to the x ln 4. That's the whole exponent. So now this x ln 4 is playing a role of x in here. So all I got to do is replace x with x ln 4, and that is my series for 4 to the x. And again, because of e to the x converging everywhere, this series will also converge everywhere. Okay, still more examples. All right, now we have a function of a very different sort. F of x is 1 plus x raised to some power k, where k is allowed to be any real number. So if I take derivatives of this function, so using a power rule, so first derivative, the k comes down, I have 1 plus x to the k minus 1. Then I take a derivative of this, so now I have an additional factor of k minus 1, and then I have 1 plus x to the k minus 2, and so on. This keeps going. So in general, here's my formula for the nth derivative, just extrapolating from all of these cases here. I have k times k minus 1 times k minus 2, all the way down to k minus n plus 1. Well, the key here is that whatever order derivative I have, that's how many factors I have here. And they all come from subtracting 0, 1, 2, etc. From k. And then I have 1 plus x to the k minus n. So then if I substitute x equals 0, I'm just going to wind up with this product of all these linear factors. So now my Maclaurin series for 1 plus x to the k is going to be this derivative value that's brought down here over n factorial times x to the n. But I can actually write this using this expression, and this should be familiar to you from some prior class. This is a binomial coefficient. So this is the definition of a binomial coefficient. Now, you may not remember this definition. The definition that you would have learned is this one. Now, when k and n are non-negative integers, and k is greater than or equal to n, this formula is equivalent to this one. But again, we don't require k to be an integer. K can be any real number. So as long as n is a non-negative integer, this formula is usable for any real number k, whereas this one would not be. So it's a generalization of a binomial coefficient that you would have seen before. So now that we have our series, we need to find the radius of convergence. So we use a ratio test. So taking the n plus first term divided by the nth term and rearranging. So this fraction here simplifies to the absolute value of x. And down here, notice we have k's canceling, k minus 1 canceling, and so forth. Everything cancels except for this, a k minus n. And then here, n plus 1 factorial is equal to n factorial times n plus 1. So the n factorial gets canceled out. Most of this gets canceled out. What remains is this factor n plus 1. So now we have this fraction times x. Now, what happens is n goes to infinity. Well, this term becomes negligible, so does the plus 1 here. So another way of putting it, this ratio converges to 1 as n goes to infinity, so you're left with the absolute value of x. But this needs to be less than 1 for a ratio test to declare convergence. So the series converges if absolute value of x is less than 1. In other words, for radius convergence is capital R equal to 1. All right. So as an example, let's look at f of x is 1 plus 2x to the minus 1/2. So k from here is equal to minus 1/2. But instead of x, we have 2x. So I'm going to make use of this Maclaurin series formula that I just came up with. So using this formula right here, k is equal to minus 1/2. Instead of x, I have 2x, all raised to the nth power. So then what I can do is use the formula for this to work all this out. So for the first term, when n equals 0, I'm just going to get 1. When n is equal to 1, I'm just going to have whatever the top number is, so minus 1/2. For n equal 2, I'll have this number plus the minus 1/2 here times this number minus 1, so that's minus 3/2. And then all of that's times quantity 2x squared. For the next term, I'll have 1/6 because I have a 1 over n factorial. And then I have minus 1/2, minus 1/2 minus 1, minus 1/2 minus 2 coming from here. So we can work out what this is, and this is the third degree Taylor polynomial with center 0. Also, these are, oh, whoops. I totally forgot. We do have more terms. These are just the first 4. And I need the same thing up here. Okay. Now, the general binomial series, 1 plus x to the k, that converges if the absolute value of x is less than 1. But in here, x is replaced by 2x. So I need absolute value of 2x to be less than 1. So radius of convergence is 1/2. So remember what I said earlier. If I know the radius of convergence for some series for f of x, if I replace x by a constant times x, the radius of convergence will get divided by that constant. And that's what happened here. Get divided by 2. All right, this is the last example I have. Is it? Yes. So now I have an indefinite integral. Sorry, not an indefinite integral. This is a definite integral, but with the upper limit being a function of x. So in other words, it is, sorry, the term I was looking for was antiderivative. Capital F is a particular antiderivative of this function, sine of at squared. So what I'm going to do is I'm going to get a Maclaurin series for capital F. So the way I would do that is I would start with sine t, its Maclaurin series that's already known. And then I replace t by 8t squared. So I'm going to get a factor of 8 to the 2n plus 1. And then since t, since I replace it by 8t squared, the power of t is going to double. So I get this t into the 4n plus 2 here. So then what I could do is I can replace sine 8t squared in this integral by this Maclaurin series. And now I can express a series for capital F of x, its antiderivative, by integrating term by term from 0 to x. So for that, all I need to do is use power rule. So I'll have t to the 4n plus 2 becomes t to the 4n plus 3 over 4n plus 3. And when I plug in the limits 0 and x, and I get this. So now, if I want to approximate, for example, capital F at a certain point, like x is 0.71, I fill in 0.71 for the upper limit. So what I could do is I can evaluate terms of this series at x equal 0.71. So in this case, what I've done is use the first 5 terms of a series and plugged in 0.71 and evaluated them. And this is my approximation of the integral. I'll admit it's not a great approximation. Okay. Well, actually, what I'm going to do is cheat by going to MATLAB. Well, it's an okay approximation. The exact value is roughly 0.2823. So at least it got the first couple decimal places right. For a more accurate approximation, I would need to use more terms than this. But this integral, as is, would be pretty difficult to evaluate. Actually, I don't think you can evaluate it using techniques you learn in Cal 2, because if there was a factor of t right here, then yes, you could evaluate that integral using a u substitution. But since you don't have that, you're kind of stuck. So this is one application of Taylor or Maclaurin series that if you have some quantity that's difficult to compute involving some function like this one, that's hard to work with directly, then you could try replacing it with a Taylor or Maclaurin polynomial of a certain degree, because for those kind of functions, polynomials are the easiest kind of functions to work with, especially for things like differentiation and integration. So yeah, so as I mentioned down here, what I did here was by using the first 5 terms, I'm evaluating approximating the integral by replacing the integrand with or not the integrand, but the integral by its Taylor polynomial of degree 19, just because 19 is the highest power of x that we have here. All right. So that's all the material that I have on Taylor and Maclaurin series. As I mentioned, this material will not be on the midterm. You will see it on the final, though, but that's a ways off. And the homework for this material that I've covered this week, and you can check Lumen, but it's due. Okay, so all of this is homework 7. That's not due until March 27th, so you have quite a while.